When it comes to our vast universe, there are a great many terms and concepts to come to grips with. One of which is black holes. The very term conjures up images of the end of life, the universe, and everything we have ever known. Black holes resemble cosmic drains, where space disappears like water draining out of a sink. Space seems to flow, and the closer one gets to the black hole, the faster it flows. At the event horizon, space appears to reach the speed of light, so nothing, not even light, can escape beyond this point of no return. Over the past few decades, we've learned that terrifying monsters are everywhere in the universe, ranging from stellar masses all the way up to supermassive behemoths. And by combining information about stars, black holes, and stellar and cosmic evolution all together, astronomers have the first robust estimate for black holes in the universe, 40 quintillion. It's more than almost anyone expected. The largest known black hole in our nearby vicinity is Messier 87, a supermassive black hole more than 6 billion times the mass of our Sun, just 55 million light-years away. From optical jets to X-ray emissions to radio lobes and even the event horizon itself, it's the best-viewed black hole ever, inside and out. However, black holes have always been these giant masses of mystery floating around in space. What we know so little about gluttonous monsters may be just the tip of the iceberg, something we've always had questions about but zero answers. But now, that's changed. Scientists finally see what's inside black hole. Join us as we dig deep into how scientists just shed light on the enigma of great devourers of the cosmos and understand their nature. In order to understand the scale of a black hole, of course, we will need to find out more about these phenomena. So, let's start at the beginning by looking more closely at what black holes are and explore some of their unique properties. The first critical point to note when discussing black holes is not to be misled by the name. Black holes are anything but empty spaces or nothingness. Instead, black holes are a lot of matter crammed into a very tiny space. For a typical black hole, imagine a star 10 times as massive as our Sun being crammed into a sphere the size of New York City. That is a lot of stuff in a relatively small container. Compressing this much mass into a small space significantly impacts the surrounding stuff around it. For example, as a result, it generates a gravitational force that is so powerful that even light cannot escape. For a long time, physicists had speculated about the possibility of an object in space so dense that not even light could not escape. This is where they get their name. Einstein's theory of general relativity, which demonstrates that when a big star of a certain size dies, it leaves behind a small, dense remnant core, is most famous for theorizing about the existence of black holes. These equations demonstrate that if the star's mass is greater than roughly 3 times that of the Sun, the force of gravity will outweigh all other forces and create a black hole. Black holes are invisible to telescopes looking for light, X-rays, or other types of electromagnetic radiation, for the very reasons explained above. But by observing how they affect nearby matter, we may deduce the existence of black holes and study them. As a result, today, black holes, invisible, impenetrable, and many light-years away, are more familiar to us than ever before. We know that supermassive versions sit at the center of most galaxies, including our own Milky Way. In 2019, we even got pictures that show a black hole as an imposing shadow against the glow of cosmic material. Scientists have detected the gravitational ripples that result when black holes smash into each other. The entire cosmos, we recently learned, might be humming with the force of such collisions. The list goes on. But the big mystery still remains. We don't know what lies at the center of a black hole, beyond the boundary where matter winks out of view forever. As Elliot Quattart, a theoretical astrophysicist at Princeton, said, The question is definitely answerable in that someone could fall inside the black hole and find out the answer. The problem is, they couldn't convey that answer to someone outside the black hole, because nothing can get out. As a result, black holes are the absolute boundary between what we know and what we don't. This is a problem that cannot be solved by astronomers, physicists, or mathematicians alone. It also requires philosophers and people who can bring a fresh perspective to these challenges, people who can push researchers to think differently. This interdisciplinary approach forces the brightest minds in cosmology to re-examine all of their assumptions. To understand why black holes scramble our understanding of cosmic forces, we need to think about their structure. If a black hole were a Ferrero Rocher chocolate ball, the first layer of chocolate and crushed hazelnuts would be the region just outside the event horizon, where gravity is still weak enough that a nearby star could safely whiz by and not fall in. Next up is a layer of crispy wafer. This is the event horizon, the point of no return. Under this layer lies smooth chocolate filling, through which trapped cosmic material is sucked toward the center. And then there's the heart of the Ferrero candy, the whole roasted hazelnut. This is the singularity, a tiny concentrated point of infinite density. Physicists believe they understand what the space beyond the event horizon, nearly all the way through the chocolate filling, should look like, based on Einstein's theory of general relativity. If an astronaut were to fall into a black hole, she would descend, and as she went deeper, she would experience the very fabric of space-time warping all around her. The 1915 theory describes well what must occur in such an extreme environment, where gravity overwhelms all other forces in the universe. The trouble starts farther in, closer to the singularity, where the laws of physics, as we currently understand them, break down. Over the years, scientists have looked into the possibility that black holes could be wormholes to other galaxies. They may even be, as some have suggested, a path to another universe. Such an idea has been floating around for some time. Einstein teamed up with Nathan Rosen to theorize bridges that connect two different points in space-time in 1935, but it gained some fresh ground in the 1980s when physicist Kip Thorne, one of the world's leading experts on the astrophysical implications of Einstein's general theory of relativity, raised a discussion about whether objects could physically travel through them. Thorne, who lent his expert advice to the production team for the Hollywood movie Interstellar, wrote, "We see no objects in our universe that could become wormholes as they age," in his book, The Science of Interstellar. He said that journeys through these theoretical tunnels would most likely remain science fiction, and there is certainly no firm evidence that a black hole could allow for such a passage. But the problem is that we can't get up close to see for ourselves. Why, as told, we can't even take photographs of anything that takes place inside a black hole. If light cannot escape their immense gravity, then nothing can be snapped by a camera. As it stands, theory suggests that anything which goes beyond the event horizon is simply added to the black hole and, what's more, because time distorts close to this boundary, this will appear to take place incredibly slowly, so answers won't be quickly forthcoming. As Douglas Finkbeiner, professor of astronomy and physics at Harvard University, said, "I think the standard story is that they lead to the end of time. An observer far away will not see their astronaut friend fall into the black hole. They'll just get redder and fainter as they approach the event horizon as a result of gravitational redshift. But the friend falls right in to a place beyond forever." Whatever that means. Certainly, if black holes do lead to another part of a galaxy or another universe, there would need to be something opposite to them on the other side. Could this be a white hole? A theory put forward by Russian cosmologist Igor Novikov in 1964? Novikov proposed that a black hole links to a white hole that exists in the past. Unlike a black hole, a white hole will allow light and matter to leave, but light and matter will not be able to enter. Scientists have continued to explore the potential connection between black and white holes. In their 2014 study published in the journal Physical Review D, physicists Carlo Rovelli and Hal M. Haggard claimed that there is a classic metric satisfying the Einstein equations outside a finite space-time region where matter collapses into a black hole and then emerges from a while hole. In other words, all of the material black holes have swallowed could be spewed out, and black holes may become white holes when they die. Far from destroying the information that it absorbs, the collapse of a black hole would be halted. It would instead experience a quantum bounce, allowing information to escape. Should this be the case, it would shed some light on a proposal by former Cambridge University cosmologist and theoretical physicist Stephen Hawking, who, in the 1970s, explored the possibility that black holes emit particles and radiation, thermal heat, as a result of quantum fluctuations. Hawking said a black hole doesn't last forever. Hawking calculated that the radiation would cause a black hole to lose energy, shrink, and disappear, as described in his 1976 paper published in Physical Review D. Given his claims that the radiation emitted would be random and contain no information about what had fallen in, the black hole, upon its explosion, would erase loads of information. This meant Hawking's idea was at odds with quantum theory, which says information can't be destroyed. Physics states information just becomes more difficult to find because, should it become lost, it becomes impossible to know the past or the future. Hawking's idea led to the black hole information paradox, and it has long puzzled scientists. Some have said Hawking was simply wrong, and the man himself even declared he had made an error during a scientific conference in Dublin in 2004. So do we go back to the concept of black holes emitting preserved information and throwing it back out via a white hole? Maybe. In their 2013 study published in Physical Review Letters, Jorge Pullen at Louisiana State University and Rodolfo Gambini at the University of the Republic in Montevideo, Uruguay, applied loop quantum gravity to a black hole and found that gravity increased towards the core but reduced and plonked whatever was entering into another region of the universe. The results gave extra credence to the idea of black holes serving as a portal. In this study, singularity does not exist, and so it doesn't form an impenetrable barrier that ends up crushing whatever it encounters. It also means that information doesn't disappear. Regardless, physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully still believed Hawking could have been onto something. They worked on a theory that became known as the AMPS firewall, or the black hole firewall hypothesis. By their calculations, quantum mechanics could feasibly turn the event horizon into a giant wall of fire, and anything coming into contact would burn in an instant. In that sense, black holes lead nowhere because nothing could ever get inside. However, this violates Einstein's general theory of relativity. Someone crossing the event horizon shouldn't actually feel any great hardship, because an object would be in free fall, and based on the equivalence principle, that object, or person, would not feel the extreme effects of gravity. It could follow the laws of physics present elsewhere in the universe, but even if it didn't go against Einstein's principle, it would undermine quantum field theory or suggest information can be lost. So, let's step forward Hawking once more. In 2014, he published a study in which he eschewed the existence of an event horizon, meaning there is nothing there to burn, saying gravitational collapse would produce an apparent horizon instead. This horizon would suspend light rays trying to move away from the core of the black hole and would persist for a period of time. In his rethinking, apparent horizons temporarily retain matter and energy before dissolving and releasing them later down the line. This explanation best fits with quantum theory, which says information can't be destroyed. And if it was ever proven, it suggests that anything could escape from a black hole. Hawking went as far as saying black holes may not even exist. Black holes should be redefined as metastable-bound states of the gravitational field, he wrote. There would be no singularity, and while the apparent field would move inwards due to gravity, it would never reach the center and be consolidated within a dense mass. And yet anything which is emitted will not be in the form of the information swallowed. It would be impossible to figure out what went in by looking at what is coming out, which causes problems of its own. Not least for, say, a human who found themselves in such an alarming position. They'd never feel the same again. One thing's for sure, this particular mystery is going to swallow up many more scientific hours for a long time to come. Rovelli and Francesca Vidotto recently suggested that a component of dark matter could be formed by remnants of evaporated black holes, and Hawking's paper on black holes and soft hair was released in 2018 and describes how zero-energy particles are left around the point of no return, the event horizon, an idea that suggests information is not lost but captured. This flew in the face of the no-hair theorem, which was expressed by physicist John Archibald Wheeler, and worked on the basis that two black holes would be indistinguishable to an observer because none of the special particle physics pseudocharges would be conserved. It's an idea that has got scientists talking, but there is some way to go before it's seen as the answer for where black holes lead. If only we could find a way to leap into one. In short, as you see, we've covered a lot of ground already, but there are many more things to learn about these strange objects. While we cannot possibly cover everything there is to know about them in one place, here is a hand-picked selection of the most interesting facts about black holes. 1. Some believe that black holes could create new universes. Believe it or not, but some scientists believe that black holes could create other universes, including our own. Leaving aside the can of worms about the actual existence of other universes, there is an entire field of science dedicated to the study of this actual possibility. An extremely condensed explanation of how this works is that, when you look at the calculations, our universe today has certain incredibly convenient circumstances that came together to generate life. We wouldn't be here if you even slightly altered these circumstances. It is theoretically possible that the singularity at the center of a black hole may shift these circumstances and create a new, slightly modified universe. Needless to say, this is hotly contested. 2. Black holes literally warp space around themselves. Like any large and massive object in existence, black holes can distort the very fabric of space-time. Sound funky? Then let's briefly explain how it works. Imagine space as a stretched rubber sheet with grid lines running through it. An item that is placed on the sheet sinks a little. When you place an object on the sheet, its sinking depth increases with its mass. The grid lines become distorted and bent due to the sinking effect. Space twists and distorts more the deeper the well you form in it. Black holes, being incredibly massive objects in a relatively small area, create localized and very deep space wells, resulting in a highly distorted portion of space. The effect is so significant that black holes can carve up a hole in space so deep that not even light has the energy to escape. Amazing. 3. It can be argued that black holes are better than suns at generating energy. Believe it or not, black holes are, under the right circumstances, capable of producing energy more effectively than a star, like our sun. But how? Well, this has everything to do with the material disk that revolves around a black hole. The material on the inner edge of the disk, closest to the event horizon, will orbit considerably more quickly than the material on the outer edge of the disk. This is due to the higher gravitational force closer to the event horizon. Due to its orbit and rapid movement, the material can warm up to billions of degrees Fahrenheit, which has the power to convert the substance's mass into energy in the form of black body radiation. What's more, this energy potential is enormous. Comparatively, nuclear fusion produces energy from mass at a rate of roughly 0.7%. By comparison, something up to 40% of the mass around a black hole is converted to energy by this process. That is, orders of magnitude more efficient. While far beyond our technological capability yet, scientists have even postulated that we could one day exploit a similar process to power starships in the future. 4. Black holes can also distort time itself. Black holes not only distort space, but also distort time itself. Consider the twin experiment, which is frequently used to clarify how time and space interact in Einstein's theory of general relativity, to see why. One twin travels to the edge of space at the speed of light, turns around, and returns to Earth, while the other twin stays on Earth. The twin who traveled through space ages far more slowly because time moves more slowly for someone moving more quickly. Due to the intense gravitational pull of the black hole, you are traveling at such high speeds as you approach the event horizon that time will slow down for you. 5. Black holes are great at creating energy, but it kills them in the end. While black holes might be more efficient than stars at generating energy, the same process may also be their Achilles heel. In theory, black holes will simply evaporate into nothingness over time unless constantly fed with mass from stars and other heavenly bodies. Although admittedly, it takes a great deal of time. Stephen Hawking initially developed this startling finding in 1974, which is why the phenomenon is known as Hawking radiation. A black hole emits Hawking radiation over a volume of around 10 to 20 Schwarzschild radii, the radius to the event horizon. Black holes decay and lose mass over time because the energy emitted by Hawking radiation slowly reduces the curvature of space around the black hole. Once enough time passes, and we're talking billions of years for even the tiniest black hole, the black holes will evaporate entirely. A sad end to one of the universe's most enigmatic objects. 6. In theory, anything could become a black hole. The main distinction between a black hole and our sun is that a black hole has a much stronger gravitational field because it is much denser. We cannot observe black holes because of their powerful gravitational field, which can prevent the escape of even photons of light. So, theoretically at least, you could create a black hole out of anything. For instance, if you compressed all of the mass in our sun into a region that was only 3.7 miles or 6 kilometers across, you would have created a black hole and an exceedingly dense region. However, there is only one known process that can create a black hole: the gravitational collapse of a star that is much more massive than the sun. So, while theoretically possible, the energy required to do so is probably only available when a massive star collapses very quickly. 7. In the end, only black holes will remain in the universe until they too disappear. As we previously mentioned, nothing can escape from inside the event horizon of a black hole, not even light itself. This led some, including the late great Stephen Hawking, to predict that black holes will be the only objects left in the universe in the far future. Long after all stars have died and galaxies have been ripped from our field of vision by the speeding cosmic expansion, only black holes will remain to show that anything ever existed. But, as previously mentioned, even black holes have an expiry date. They too will cease to exist. The projected time required for the most gigantic black holes to disappear is 10 to the 100th power years, or 10 with 100 zeros after it. That is a very long time, but it is not forever in the grander scheme of things. And so, after a dramatic start and a good run, eventually everything in the universe will, for all intent and purposes, cease to be. Nice. And that is your lot for today. Black hole boffins. Since they were first postulated in the early 1910s, black holes have fascinated scientists and the public in equal measure. A popular subject for science documentaries and entertainment for many decades, we still know very little about them today. If our species survives long enough, we may one day harness their very power to explore the universe before it all disappears forever. Unless, of course, we are all consumed by one first. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.